use of the OMC with the carbon nanotubes, it might be more conductive. And the other approach that we have in our mind, but we have not started yet, is to use carbon nanotube instead of the sucrose. And we fill the silica template with carbon nanotubes. We make them take the shape of the silica, and then we at this time we'll have a conductive type of carbon. But this method is really difficult to control, so we'll leave it for the last.
So how much of nickel?
So first, we tried this one, and we got really exciting results. We started with 10% nickel oxide on the SPA50, and we got really nice performance. Now you see the ohmic polarization of our new material is pretty close to the carbon black one. While the mass concentration, mass transfer polarization, you see that we got even better performance than the carbon black because of the high surface area of our new support.
So the red one is your OMC, yeah, I see.
The red one is OMC. You see the OMC in the ohmic polarization region, we have lower, we have more like voltage drop, but it's pretty close to the carbon black. But when you go further with increasing the current density, we get much better performance when we use the ordered mesoporous carbon, and that's because of the high surface area of the carbon, so that the reactants will diffuse easily and react. And we use the same operation conditions.
So this is consistent with your expectation?
Yes.
Because the higher surface area.
Yes. This proves that like if you change the support to higher surface area, you get better, you get easier reactant diffusion, and also you get a better platinum dispersion. And I will show you that in the.
So you need 20% of platinum or 20%?
20% platinum in each case.
And how much is nickel?
The nickel we started with 10% nickel oxide on the SPA. But actually what's happening, we don't know yet what's the exact mechanism that made this enhancement in the conductivity. So first, when we started, we got this idea because we saw that people use the nickel oxide when they prepare the carbon nanotubes. So we thought that this method will increase the crystallinity of the carbon. But then we did the XRD test, and we did not see any peak for any crystalline carbon. So I personally think that this is what's going on. We have some nickel.
That's when I agree with your personal thinking.
No, there might be two possibilities. We haven't checked it yet, the detailed characterization. There could be a microcrystallinity, because even though we had very high surface area OMC, we didn't get any performance. But the moment we had the SPA with the nickel, we got very good performance. But when we added extra nickel to the existing OMC, that blue line, we didn't get that performance. So the presence of nickel is not improving the performance.
Yeah.
So the presence of nickel during the carbon synthesis is playing some role. So that could be the improvement in the properties of the OMC, maybe the microcrystallization. Even though we didn't see the proper peak for the crystalline carbon, but there might be some microcrystallinity. That's what right now the prediction is.
Yes, that could be another.
Yeah.
So what I'm thinking is that here we have some nickel particles on the silica, and some of this nickel particle will be inside the pores, or will be on the surface of the pores, or it will be within the silica structure. So once we impregnate the silica with the sucrose and carbonize, I think that we will be left with some nickel particles inside the pores and between the carbon rods, and that's what's causing the higher conductivity of the material. And also we did a TGA analysis for the material, and we saw that after starting with the 10% nickel oxide, we end up with only 5% nickel oxide after the synthesis. Which means that some of the nickel that was within the silica structure was washed away during the template removal. So,
Wait. Is it removal or you're not losing any nickel while you're heating it up so much?
yes,
Because the nickel carbon, I don't know. Is there any possibility you can make nickel carbonyl? Because if you make nickel carbonyls or anything, that can vaporize away when you go to the high temperature.
That's what we are doing. We are trying to remove all the carbon under air environment. At that temperature, we will not see any carbon.
But then it can form nickel carbonyls. If you have suddenly not, I
Even
don't know how
at
tell you.
1000 degree, I don't
Is it
think
like a solid-
nickel carbonyl
solid
also will be stable.
You know, it will vaporize.
I mean this.
Yeah.
I mean even if I'm not really sure, but
Yeah, you're just removing all the carbon.
Yes.
yeah, I don't know. This one is a really good point that we need to think about.
Nickel
There might be
may
some
you have
other
to-
compound that's from.
Yeah. So be very
Nickel
careful.
carbon.
Carbonyls are very poisonous. It's just, you're doing the completely
Nickel
the food, right?
it's a volatile compound.
We're using very small amount of.
Carbonyl has a bad reputation, okay? You could be dead on the floor. Carbonyl poisoning. Do some.
Do everything in the food.
Look into the safety and other things. So, in pure you have to run the experiments. So just don't assume it's small amount. No.
Just to point out, it's as low as 10 milligrams.
Yeah,
It's
okay,
very
it's-
tiny amount.
So, but it's stable, very stable until almost 400,
Yeah, I mean, after 500,
450 degrees or so, very stable.
after 500. So, yeah, the material is pretty stable.
This is the common method used to find out the actual metal content in the carbon, because you can burn off carbon easily. So fuel cell research they use this easy method. You don't need to react or ICP to find out the actual total metal loading. You can just remove the carbon under air environment and you left with the metal.
So I think that's what's going on, and that's what's increasing the conductivity of our material.
Very interesting. Yeah.
But I mean, if you go back here and we do more research, if we can make this conductivity goes even higher, then we will be able to use, we will be able to reduce the amount of platinum loaded on our catalyst while getting the same performance.
But you know, if you can really improve the performance, I think even that's very good. You can get a science paper. If you can.
Actually, nickel is a very good graphitization catalyst. So we were actually expecting that we have graphitic walls of the carbon. The OMC has very high surface area, but the walls are amorphous,
Yeah.
and we can't put, because we use Nafion to improve the conductivity of carbon. But because of the pore size is very small, the Nafion can't go in there, and so the conductivity is a big problem for the OMC. So we're trying to improve the walls itself, so we can get the graphitic wall which are very conductive.
And just to finish what Deshmani started, that's why we want to use the carbon nanotubes instead of sucrose in the synthesis.
I have another question. Maybe you know all this. I haven't read it yet. Why people don't use MCM41 over SBA15 for making the template?
MCM is not having interconnecting
It's been
pores.
used actually.
So the stable would,
Yeah, they use that.
Yeah, but
we used, but we didn't get the order structure.
no, actually we used 41.
Yeah.
We used the
Okay,
original
41.
paper. They predicted that MCM 41 will not be stable.
Right.
Yeah, that's why it's not having interconnecting pores.
But people used MCM 48.
MCM48.
Yes, I'm not sure if they use it in the fuel cell applications. That's the.
Because you know they have
48 and
it has higher surface area than SBA15 actually.
yeah, but it doesn't have the interconnecting pores, because we found the rods, but if they are not connected to each other, they break away.
That's the point.
So he show the mechanism. Can show the mechanism. You see those small rods which are connecting
These are channels. These are responsible for the high.
those are not
surface area.
available in the MCM.
Okay, that's the point.
So, for
Yeah,
any reason,
I don't know whether the students get the point. Maybe you tell it. Yeah. You know that those of you who have attended the first lectures, the presentations, Richard and Srilanka, they're primarily working with MCM 41. That also has very high surface area, but it's a different structure compared to SBA 15, and that's why it is not considered for making this OMC. the mesoporous carbon.
And just to point out for the new fellows, these channels is what's responsible for the high surface area of our material. Because, like, think about this as a carbon rod, carbon rod, carbon rod. If there is no channel between them, there will be no pore here. So these pores are these channels are very important to obtain the pore after the carbonization. Okay, so after we finished with the polarization analysis of our material, we did a cyclic voltammetry analysis.
Oh, you guys have CV set up now?
Yes,
That's part of
this
the
is
basic station.
yeah. I'll
That's a $50,000 piece of equipment, this tiny
I
piece.
have to see this.
yeah, actually, we have two machines to run CV. We have the Autolab and the
Yeah.
fuel cell testing
There
station.
is other person, he has CV and impedance set up.
Oh,
If
okay.
you need any impedance analysis.
Yeah, actually, our
Yeah,
fuel cell station
you
we
should,
can do
you should
the.
talk to Smith
Yeah.
and Dr. Shah.
Actually,
Yes,
yeah.
yes.
Our
We don't have a lot of them. We have
I'm sorry.
Yeah, we have crucial research.
Crystal applied research lab.
Okay.
I've used AutoSAR before.
Yeah, I have a question. How do you use Autolab? You use just Autolab and monitor to the computer, or just use Autolab plus something? If you
You mean the software?
Yeah, I know you have to use the software and Autolab. Yeah. Only the machine Autolab you're using, or you have to?
An AutoLab is, you need some kind of fuel cell setup. The instrument is just going to applying some voltage or measuring some current. That's what it does. And it also does some signal processing.
You need a 3 electrode cell.
You need the electrode setup.
We call it 3 electrode
This is
cell.
what it will provide.
So we run the cyclic voltammetry analysis for our material to evaluate how much platinum was actually used in our catalyst. How much platinum is actually participating in the reaction. So from the CV test, we are interested in this area, the hydrogen reduction region. If we integrate this area, we will get the reduction charge density, and if we plug it in this equation, we'll be able to evaluate the surface area of the platinum is actually participating in the reaction. So we run the CV test for our material, the carbon black, the other mesoporous carbon, and our new modified material, and we did the calculation on this region. And for the carbon black, the 20% platinum of carbon black, we found out that the surface area of the electrochemical surface area of the platinum is 55.5 meters square platinum per gram of platinum. While for the OMC only, we got only 34.7 meters square platinum per gram platinum. But when we used our new material, we got even higher platinum surface area, because the high surface area of our support was the reason for better dispersion, better platinum dispersion. So now we have more platinum participating in the reaction.
Now, how reliable these numbers are, and how reproducible?
Actually, I matched this number with the literature, and I get like pretty much close to the literature. So I did the same calculation using those material. I don't know how good will it be. I haven't reviewed
That's the first time we have done that.
Yeah, but when I did it on the carbon black, I got pretty close numbers. Like one of the papers I've seen, they got 53 point something meters square platinum. So I assume my calculation is proper.
No,
when I use the.
carry on. I'm just wondering.
So that's pretty much it, what we have done so far. We used this fuel cell testing station in the polarization test and the cyclic voltammetry, and we also, this piece of equipment will allow us also to do the impedance test. And for the OMC synthesis, we use this high temperature furnace, and we feed the nitrogen here. And if we made a side valve, if we want to grow the nanotubes that goes to a benzene bubbler, where we can vaporize benzene and use a mixture of benzene and nitrogen to grow the carbon nanotubes. So, yep.
Can you show your fuel cell on that?
Now for your carbon nanotubes, do you have any PEM or?
We have XRD.
Huh?
Sure. We have taken XRD.
It did show, but it didn't work for the fuel cell, so we kept it aside for the time being. So we thought, let's do.
We don't want to talk about it right now.
What's happening, Doctor, is this the nanotubes requires lots of empirical
Yeah.
tests to adjust the
Get it
vapor,
right,
the
yeah.
benzene vapor. We tried like to distillate the benzene and see how much,
Yeah.
what's the flow rate.
Yeah.
And
And
it's,
you're doing everything in the hood, right? Everything.
Yeah.
Benzene you do not.
yeah,
Handle it.
What type of carbon nanotubes was that?
I'm not really sure. I'm not familiar.
That's why I was asking about
Not
the
that much
structure.
study.
But all we saw in the XRD is we have a crystalline peak. We have a peak for a crystalline carbon. Not really
Is
sure.
it
I'm not
commercial?
really familiar.
Commercial. Yeah, commercial.
Sorry.
Yeah, carbon nanotube, we got a commercial carbon nanotube.
It's a commercial.
Are you growing it or it's commercial?
No, I'm growing.
Yeah.
This is the setup where I grow it. See, I feed the nitrogen into a bubbler to obtain and like adjust the operation parameters to get 10% benzene and 90% nitrogen. And I use nickel catalyst to grow these now.
So it's like CBG method?
Exactly.
This is CBD. Yeah.
Chemical vapor.
Homemade
So you're
CBD.
growing, okay.
So that's pretty much
Yeah.
our presentation.
Very good, very good. Any questions for? Any questions? Any comments, suggestions?
I need to go. I need to go by 5:30.